vapor cycle. This is under thermodynamics and heat transfer. This is for our first problem for our part 1. A steam power plant is proposed to operate between the pressures of 10 kilopascals and 2 megapascals, worth a maximum temperature of 400 degrees Celsius. So, we need to find for the maximum efficiency possible from the power cycle. So, what is the maximum efficiency possible from the power cycle under operating pressures of 10 kilopascals and 2 megapascals with a maximum temperature of 400 degrees Celsius? So, first up, at 10 kilopascals, we need to use our property table and charts because we need to find for the initial and the final specific enthalpy of the following saturated liquid. So there is property table involved here because we're dealing with steam power plant and it is a vapor cycle. So at 10 kilopascal pressure here, you can see here 10 kilopascal pressure, we're going to find the corresponding initial and final specific enthalpy of the saturated liquid. So we have here the encircled one. We have the saturated liquid to be 191.81. So with our S3 here, it is given, no? So solving for the pump work. Solving for the pump work, we have this formula. The work of the pump is equivalent to the initial V, the initial saturated vapor multiplied to the difference of the initial and the final pressure. That is 2000 kilopascals and 10 kilopascals. So we have now the work the work of the pump to be 1.99 kilojoules per kilogram. So let's proceed to solve. It is here our saturated liquid. It is on this property table denoted here under 10 kilopascal pressure. After getting the value for our pump work, so let's proceed using this equation. We have here inside this parenthesis, we have the specific heat minus the pump work is equivalent to the difference of the initial and the final specific enthalpies of this substance. So we have here this equals to the initial enthalpy, specific enthalpy plus the work input in our steam power plant. So we have here the 191.8 kilojoules per kilogram. So it is located on our steam table a while ago. I have shown you here. Plus the work input of the pump to be 1.99 kilojoules per kilogram. So after that, let us calculate for our final specific enthalpy. We now have the specific enthalpy to be 194 kilojoules per kilogram. So let us check our calculator. Please solve. Yes. For our heat input, we have here the specific heat is equivalent to the initial differences of the specific enthalpies at process of 2 to 3. We have here the heat at B to be 3248 kilojoules per kilogram minus 194 kilojoules per kilogram to be the heat input is 3054 kilojoules per kilogram. For our state 4, our entropy for state 4 and state 3 is equal. So it is given on our first slide, or on our second slide, the entropy on our process 3 to 4 is equal 37.1 to 79. Solving for our entropy at state 4, we have here the final entropy plus the final specific entropy plus our quality X at process 4 and the difference between the saturated liquid and vapor of our specific entropy. We have here 7.1 to 79 is equivalent to 0.6491 for our saturated liquid of specific entropy plus this the difference between the saturated liquid and vapor of our specific entropy 7.519 multiplied to our unknown quality X at state 4. We now have the quality X at state 4 to be 2259 kilojoules per kilogram. So let us proceed. For the work output from the turbine, the work output from our turbine, we have here, it's denoted the small letter W. T is equivalent to the specific enthalpies at process 3 to 4. So we need to subtract these two values in order for us to find for our work output from the turbine. That is 989 kilojoules per kilogram. After finding or solving for the work output from the turbine, we have the efficiency formula. That is the difference between the work output of the pump, the work input from the pump, and the work output from the turbine all over the heat input. So that's it. We now have the efficiency to be 0.3232 or 32.32%. That's it for part 1 problem in our vapor cycle under thermodynamics and heat transfer. Thank you so much for listening and for supporting this video. And see you on our upcoming videos to come. Have a good day.